We proudly present a lot of Gaussians. 3D Gaussian splatting has shown remarkable speed and accuracy in the task of novel view synthesis for object-centric and small scenes. However, city-scale reconstructions with scenes like this remain an open challenge. The big issue is storage. For every Gaussian, we need to store position, scale, rotation, and color. Additionally, spherical harmonics coefficients are required for view-dependent color. The Atom optimizer triples that amount with its momentum parameters. Finally, we need to store the gradients of all properties, resulting in up to 780 bytes of VRAM just to store a single Gaussian. The rendering and training process roughly doubles this amount again. This sets a clear limit on the number of Gaussians that can be trained simultaneously on a single GPU, about 500,000 per gigabyte of VRAM. Other works have already identified that for large-scale scenes, increasing the number of Gaussians is the key. The solution is often to use more hardware. The shown scene was trained on 64 A100 GPUs running in parallel. The most popular approach to lower these requirements is the divide and conquer strategy, where the scene is first split up into chunks, which are all trained separately, and finally fused back together. Countless different strategies of selecting chunk boundaries have been proposed. But the approaches still suffer from fundamental flaws. Chunks may have visible seams at borders, intrude on neighboring chunks, or train ghostly structures that are actually contained in a completely different chunk. These artifacts can be minimized by using well-behaved training data, like single-height aerial photography or single-path street-level images. Combining the two or including less structured views into training will break many state-of-the-art large-scale reconstruction methods. But there is an even more fundamental problem with divide and conquer. While only loading a single chunk is okay during training, when the scene is rendered, all chunks may have to be present in memory, dramatically increasing VRAM requirements. So, what would it take to train and render ultra-large-scale scenes with arbitrary training views on consumer-grade hardware? Let's say these blocks represent our Gaussian data that is being optimized on the GPU. Let's move them over to RAM to avoid exceeding our VRAM budget. Typically, only a small subset of Gaussians are required to render a particular view. We load this subset into VRAM before our training iteration, and then write the optimized Gaussians back to RAM. Still, a single training view could require all of the Gaussians to be present on the GPU. But that also means that the view is quite far from the scene, and we can use a level of detail system to select a manageable number of Gaussians to train for this view. Our LoD system is based on a binary tree, where the leaves store the finest detail Gaussians, and any parent is a rough approximation of the sum of its two children. Any cut of this hierarchy then represents the set of Gaussians that are required to represent the scene at a particular level of detail. Training directly on a level of detail structure means we cannot ensure that parent nodes are always bigger than child nodes, which makes naively computing the LoD in parallel unstable. To remedy this, we use the sequential point tree data structure, which is lightweight, efficient, and robust to changes during training. We store the entire Gaussian hierarchy in RAM and convert subtrees into storage-efficient sequential point trees, which are used to compute LoD cuts on the GPU. When increasing the Gaussian count during training, we have to keep the LoD hierarchy stable. The densification process occurs on the CPU. New Gaussians are added as children to leaf nodes. Gaussians that are no longer required are moved to another part of the scene, while ensuring integrity of the LoD hierarchy. Finally, the sequential point trees are recomputed and training commences. Constantly transferring Gaussians between RAM and VRAM slows down training. Therefore, we keep a cache of Gaussian patches with a particular level of detail on the GPU, so it can be reused between iterations. We select training views such that subsequent iterations show a similar portion of the scene. Using a random walk procedure for the selection prevents overfitting while optimizing cache utilization. In summary, our overhaul training pipeline enables training and rendering of massive scenes with 150 million plus Gaussians on a single consumer-grade graphics card, without any artifacts from chunk division. We verify the effectiveness of our method on kilometers of street data.
And giant complexes. As well as huge virtual cities.